awarded Nobel Prize in Physics in 1930. In 1986, the NCSTC asked the Government of India to designate February 28 as the National Science Day, and that's why we are celebrating it to widely spread the message about importance of science used in daily life of the people, and also give an opportunity to the scientific minded citizens in the country and encourage people as well as popularize the science and technology. On this occasion, we have very established scientist Professor Dipankar Banerjee as our chief guest, and it's my privilege to welcome you, sir. He will be taking he will be talking on the interesting subject materials for flight, which is very important for our organization. I also welcome Advisor M&A, Advisor W&S, ACSR lecture speaker Dr. Ramesh Sundaram, Head 4PI, and students of and all my senior colleagues as well as friends over here. Dr. Ramesh Sundaram will be talking on structural health monitoring of composites. I take pleasure to introduce our chief guest, Professor Dipankar Banerjee. Dr. Banerjee graduated from IIT Madras and obtained his PhD from Indian Institute of Science. His early research career involved understanding structure property relationship in titanium alloys using advanced techniques of electron microscope, and subsequently the development of intermetallics based on the titanium aluminum system for use in high temperature applications. As the director of DMRL, Dr. Banerjee provided leadership for many critical defense-related materials programs, including special naval steels for Indian Navy's aircraft carriers, investment casting processes for single crystal, directionally solidified and aqueous Ni-based alloys, and the development of titanium alloys products for aero engines. As the Chief of Controller R&D of DRDO, he coordinated military engine and combat aircraft programs. He was coordinating LCA program very actively, and major system development efforts he has taken in airborne electronic warfare, unmanned vehicles, and airborne early warning capabilities. He also conceptualized new materials program for application at ultra high temperature stealth and electronic devices. Dr. Banerjee is a fellow of all the Indian Science Academies and the Indian National Academy of Engineering. He has been recognized as the Distinguished Aluminium of Indian Institute of Technology, Chennai, and Indian Institute of Science, Bangalore. He has been awarded the Shakti Swarup Bhatnagar Prize in Field of Engineering Science, DRDO's Lifetime Achievement Award, and Padma Shri, and many more. I think because of the time constraint, his contribution is enormous to the country, and we are very fortunate that today he will be giving us avenue on materials for flight. Welcome you to sir once again, and over to you, sir.
Well, first of all, thank you for inviting me to this National Science Day talk. I must apologize for not being there in person. When I was first told that it was a webinar, I had fixed up a meeting at 3 o'clock. And so it would be impossible for me to come back and participate in that meeting. And so I must apologize for not being at NAL. It is a pleasure for me to participate in this function at NAL particularly. And there are quite a few reasons for this. I have, of course, known Director Sri Jadhav for a long time, since he was in ADA. But my association with NAL goes a very long time back. In fact, my first job ever was actually as a daily wage laborer in NAL. And this might surprise you. But I was doing a summer internship with Dr. Arunachalam, former head of DRDO, who was then in NAL. And Dr. Arunachalam found an innovative way to pay us. So he signed us on as daily wage laborers so that we would have some pocket money to play with. And that, as an undergraduate student, was actually very nice. After I finished my BTech, I joined the Indian Institute of Science for my PhD, and one of my advisors was again Dr. Arunachalam. And so for the first year or two of my PhD program, I was actually sitting at NAL starting my research work. And it turns out during that time, I even played cricket for NAL. I think it was in the second or third division league cricket in Bangalore. And I remember some of my fellow players whose names you may recognize, some of the people who've been at NAL for a long time, Rajaram Nityananda, Ramesh Dharam, Joe Pichamuthu, who was, I think, the captain of the cricket team. And finally, I was actually offered a position at NAL, but I didn't take it because I joined DMR. So these are fairly intimate connections. And so again, I'm delighted to be here with you all. But on to today's talk, which is really based. So on to today's talk, which is really based on my experience working for the DRDO. And underlying that is the experience of material science and engineering, which is my profession. And I suppose I'm talking to an audience that varies enormously in terms of professional background. So what I'd like to do today is to outline what we've done for aeronautical materials in this country, but also talk a little bit about the underlying material science and its paradigms. So with that, I intend to start with a very brief historical background about materials engineering. And the starting point is this Greek myth, and which tells you something about the early intimations of materials criticality. So Daedalus in this myth and his son Icarus were imprisoned on an island, and to escape, the father Daedalus fashioned for Icarus these wings made of feathers and wax. And when they were ready, he told Icarus that when you fly, you can't fly too close to the sun because the wax will melt. And you can't fly too close to the water because the wax will absorb moisture and become too heavy. But when Icarus started flying and found he could fly in his youthful enthusiasm, he flew higher and higher too close to the sun, and the wax melted and he fell into the sea and died. And so this is a nice parable about materials engineering. It tells you something about the properties of materials, in this case, wax. It tells you something about the designer intent and the boundaries within which the materials can be used. And it tells you something about human error as well, because unless you function within the parameters set by the design and the materials, bad things can happen. So this is a good way to understand materials engineering as it is today. But I also want to remind you that metallurgists, materials people and metallurgists in particular, belong to one of the oldest professions in the world. So first of all, the first great innovation, metal forming, was about 4000 BC, where we learned to soften the native copper, to shape it and to harden it. The second great innovation involved extraction of copper from its ore, and this was in Israel, again around 4000 BC, using iron ore as a flux and ways to melt this and draw the copper ingot out. And the third great innovation was alloying, in which we learned that tin strengthens cast copper and improves what is today known as bronze. Okay, again around 2000 to 3000 BC. So it's pretty humbling to note that the paradigms in which material science is based, that is the relationship between processing, structure, composition, and properties, these paradigms were actually discovered something like 6,000 years ago. I used in the previous slide the idea of structure, and I must talk a little bit about structure, because this is something that most engineers do not recognize as a central feature of materials engineering in this connection between composition, processing, and properties. If you look at a piece of metal, it appears featureless. But somewhere in the 17th or 18th century, we found that if you prepare the surface of a metal properly, you begin to see features in its surface. And we found that these features actually represent grains or crystals which are oriented in different ways, okay? And so you can see today structure at the scale of tens of microns, which could be the grains in the material. You could see the distribution of crystallites within grains, which could be as fine as 10 to 100 nanometers. You can even today, with modern techniques, see the distribution of atoms within these crystals. So we can see structure at different length scales. We can also see structure when we combine microscopy with spectroscopy. We can see chemistry at this nanometric scale. So we can see the chemistry of individual crystals. We can see the chemistry actually of individual atoms. And through atom probe tomography, we can see distribution of chemical elements in a three-dimensional sense. And so this very important evolution in our capability to look at what we call microstructure is an important part of the material science paradigm. The other part of this paradigm is our understanding of how defects in materials interact with the material structure as I described it in the previous slide, to provide the two aspects of metals and alloys that we are interested in application. One is the toughness or plasticity in the material, which is actually achieved by the motion of these defects that are called dislocations in the material, imaged here at transmission electron microscope, and the restriction of the motion of these dislocations in multi-phase materials to constrain the motion of the dislocations, as you see in this slide, it provides strength in the material. So this interaction between defect structure and microstructure to determine properties is a key element of structural materials. We have learned how to process materials at an enormous variety of length scales. 30,000-ton forging presses, for example, are used to make shapes and sizes used in, let's say, thermal power plants. We can use additive manufacturing to get extremely complex shapes without machining. We can manipulate materials at the thin film level to form integrated circuits. We can form organic, inorganic hybrids, and we can actually manipulate atoms. So this entire range of scales is now available to us as materials engineers to shape the kind of material that we want. And we combine microstructure and this ability to manipulate shape with something that we call architecture. And we have learned to control the architecture of the metal at a micrometer or nanometric scales. We have learned to understand from biological structures, natural structures, how hierarchical structures offer new properties. And all of these can interact with the object that we are trying to make finally to provide the kind of properties that we want. And so materials engineering deals with materials at various length scales, but treats materials as heterogeneous aggregates of crystals, of chemistry, of atoms, and so on. And it interacts with the mechanics of materials, which, let's say, aeronautical engineers or mechanical engineers use, which treats the material as a continuum to develop structural properties or to design structures. So this interface between materials engineering and people who do mechanics of materials in developing structural integrity is an extremely important interface, and it's important that there is an understanding on both sides of this divide on the way materials engineers and mechanics people deal with materials in designing structures. It's important also to understand, and I think this is not very well understood in the materials, in the non-materials community, that in very conservative applications, such as aeronautical applications, it takes an enormously long time to develop new materials. In fact, this article from GE Aviation points out that if you want to introduce a new materials class in an aero engine with no prior application experience, this might take typically 20 plus years, okay? And even the modification of an existing material for a new critical structural component might take you up to 4 to 5 years. So what do we do about this? How do we accelerate the insertion of materials into service? In the past, metallurgical knowledge or materials engineering knowledge has been primarily based on empiricism. And much of the time has gone into developing databases related to joining, repair, machining, non-destructive evaluation at process scales that are important for design and application. What materials engineers are now trying to do is to combine their knowledge of the physics of the material into computational material science and engineering methods, such that you combine these computational and simulation methods with verification and validation, characterization, sensors, and so on into an integrated computational platform that will allow you to enable early insertion of materials into service. So this is where we are headed. And now if you look at aeronautics and the role of materials in aeronautics, we start by looking at energy efficiency in aviation. So over the years, and we have achieved actually enormous improvements in energy efficiency. Here looked at in terms of the aircraft fuel burn per seat, in terms of the base level of the first jet aircraft, which is the Comet. We've improved energy efficiencies by about 70%. And part of this energy efficiency improvement comes from the thrust-specific fuel consumption improvement in jet engines, in different designs of jet engines. A typical combat air patrol of the Tejas, for example, with let's say a radius of action of about 200 kilometers, will use about 4,500 kilograms of fuel. And a 10% increase in structural weight will provide about 2.5 to 5% increase in fuel efficiency. So amongst the various factors that affect aircraft energy efficiency, materials, the contribution of materials, apart from performance itself, lies in possible weight reductions and in performance through, let's say, engine thermodynamics, which allows you to improve engine operating efficiencies. And of course, combat performance, so the metrics of combat performance are also determined by structural weight. And so if you look at airframes, typically, the material that you use in airframes depends on the sustained Mach number of the vehicle that you're applying the material in. So therefore, for high subsonic and low supersonic flight, you're happy to use polymer matrix composites or aluminum because the skin heating due to that Mach number is limited to about 150 degrees centigrade. As you increase the Mach numbers, the skin heating becomes higher and higher, leading to higher airframe skin temperatures, and you have to graduate to different kinds of materials. And this therefore fundamentally determines the kind of materials that you use in an airframe. So we start from aluminum used in the First World War to composites, which are now used in military and commercial aircraft. This is the only aircraft that ever used a titanium airframe, that's the SR-71, which flew at Mach numbers of about 3.2. And finally, for hypersonic systems, you have to look at these refractory materials based on carbon, silicon carbide, and so on, and various thermal protection systems. I will not talk much about aluminum because aluminum has really given way to the composites in critical fuselage applications because of the lower density of composites as well as their capability to function in environments that have moisture in them, corrosion resistance, and so on. But I want to illustrate this example, use this example as an illustration of the relationship between science and engineering. So the basis for aluminum production was in 1886. And the first aluminum copper alloy, what is known to material scientists as the precipitation hardened alloy, was discovered in 1906. This material was used by the Germans in their First World War military aircraft by 1915. But I want you to note that the understanding of the phenomenon of precipitation hardening from a material science aspect evolved over the next 50 years. Okay, far long after it was used in application in 1915. And so, therefore, this relationship between science and engineering is not really linear. Science supports engineering, engineering enhances scientific knowledge or drives scientific knowledge. And indeed, this improvement in understanding has led to evolution of aluminum alloys with properties well beyond that of the first precipitation hardened aluminum alloy. But now, of course, composites have taken over as airframe materials in subsonic aircraft and so on. And talking about composites at NAL is really like, I mean, you all are so familiar with composite development and manufacturing is a part of NAL. But what I do want to point out is that there are opportunities for new integrations of material synthesis and design, because you can manipulate composite structure. Okay, you can architecture the composite structure so as to obtain the precise kind of microstructure that you need for the local stresses that the material structure will experience. So, for example, bamboo has a higher density of fiber at its surfaces to withstand higher tensile stresses at the surface of the bamboo when it waves in the wind. The other opportunity which composites obviously allow or enable is the embedding of smart sensors and actuators combined with structural design that will allow parts to meet complex multifunctional requirements. So self-healing and damage assessment. And this slide is really an introduction to Ramesh Sundaram's talk later on. I want to talk briefly about stealth while I talk about airframes. Much of stealth is confirmed by shaping the vehicle, as you know. But even as you shape the vehicle, you remain hotspots in terms of radar reflection remain in terms of, let's say, engine intakes or outlets and so on. And you will need materials to provide radar absorption to accommodate what you can do with shaping. And these materials then can be very effective, as shown by this near field description of radar inflection with facilities that are available at the Defense Laboratory in Jaipur. And the varieties of materials that can be used in stealth applications are actually quite enormous, but they can also add to weight. So, for example, high levels of stealth can add 15 to 20% of structural weight. So the drivers for stealth are certainly density reduction, but beyond that, broadband absorption capability, mechanical strength, and perhaps frequency selective adaptive protection. And the physics of stealth materials is really determined by the physics of electromagnetic wave interaction with the materials. But while understanding the physics, one has to look at the environment, the adhesion of your stealth material to the airframe structure in response to mechanical stresses, temperature, and moisture as well. So the engineering of stealth materials and coatings into airframes is a whole new activity by itself, which we've been doing both in DRDO at NAL now for quite some time. I move on to the aero engine. The aero engine is really an extreme environment for materials. Aero engines operate with revolutions of the discs, blades, and shafts at greater than 10,000 revolutions per minute, leading to fatigue. High temperatures lead to oxidation. Birds, sand, and ash ingestion at high velocities lead to various forms of impact damage. Moisture, impurities in the fuel, and so on can lead to corrosion and erosion. And so this is truly a difficult, to my mind, one of the most difficult environments for materials, both in terms of design, application, and life. And three typical classes of materials are used in aero engines. One is titanium, which is used in the front parts of the engine, the fan and the compressor, to about 550 degrees centigrade. Nickel-based alloys, which are used in the hottest parts of the engine beyond the combustor, that is in the turbine, where temperatures can rise as high as 1600 degrees centigrade. And then there is the gradual increasing use of ceramic matrix composites right now in the rear of the engine as convergent, divergent flaps and so on. Remember that the engine thermodynamics and efficiency depends on the Brayton cycle, the thermodynamic cycle known as the Brayton cycle. So higher the temperature that you can drive the turbine at, the higher the efficiency of the engine. So I'll talk a little bit about turbine materials and particularly the turbine blades and vanes that are used. And today's nickel-based alloys, and remember that the temperature capability of these turbine blades and vanes determine what can be used as the turbine entry temperature and therefore the engine efficiency. Okay, so the temperature capability of today's nickel-based alloys is around 1100 degrees centigrade. The turbine entry temperatures in today's engines are about 1600 to 1700 degrees centigrade, and actually are above the melting point of the material, which is typically around 1400 degrees centigrade. So how do you use material which has capability about 1100 degrees centigrade, which itself is a reasonable fraction of the melting point, but there is this huge gap which we have learned to overcome. And we've learned to overcome this by internal cooling of these blades and vanes so that the blades are hollow and have these complex channels into which cooling air is driven, taken away from the compressor of the engine. And finally, you also coat these blades with insulating thermal barrier coatings, usually zirconia or a form of zirconia, together with an oxidation-resistant coating that lies between the substrate and the thermal barrier coating. So this is a complex material system which allows the operation of these materials well beyond their melting point. And so we have to understand the substrate metallurgy. And part of that metallurgy is the improvement we have achieved in these materials through the casting process. And the casting process is required because we are making these complex hollow castings with the internal cooling channels. So we have gone from castings in which the grains are equiaxed in shape. You can see these fine grains here, to grains that are columnar in shape and oriented along the loading direction in operation, such that there are no shear stresses acting on the grain boundaries. And then finally, single crystals, which eliminate these weak grain boundaries altogether. So that is one part of the improvement that we have achieved. And this technology of making single crystals is, to me, one of the most marvelous forms of materials technology. There is, first of all, the design of dies for the casting, for these complex aerofoil shapes. Incorporating ceramic cores, which will provide these internal cooling channels in the blade. And then you inject wax into the die to get a shape which resembles the external shape of the blade. And then you dip this whole thing into a ceramic slurry and fire it. And then you remove the wax by steam. And finally, then you have a hollow ceramic mold with the core inside that is shown in a cutaway form here. And you pour metal in a furnace into this little hollow over here. And you control the thermal gradient such that the heat direction is unidirectional to provide you with the columnar grain structure or even the single crystals. Okay. And this is a truly complex technology. You think about it, you're pouring metal at about 1400 degrees centigrade into these hollows which resemble this blade shape, which are sometimes less a millimeter or less at the leading edges. And you have to preserve the integrity of the ceramic mold in the core when you're pouring at 1400 degrees centigrade. And you have to accommodate anisotropic metal shrinkage, core shrinkage, mold shrinkage to achieve the final tight tolerances which the aeronautical engineer requires in his aerofoils. But we've learned to master that technology as well. We've also learned how to improve or understand the metallurgy of the substrate material, which is made of this what we call two-phase material, consisting of a disordered FCC phase and an ordered FCC phase. And if you look at the high-resolution structure of this phases at the interface here, you see that various metals that constitute this single crystal turbine blade are certainly not uniformly distributed. They're distributed differently in this phase and in this crystal, and they're not distributed uniformly within each crystal either. There is segregation of various kinds. And we have to understand the motion of dislocations or defects that I talked about within this very complex structure and chemistry. And so this is the understanding that material scientists have been developing at this scale of microstructure, which finally feeds into the properties that mechanics people use in the design of these aerofoil blades. And remember, as I said earlier, that the materials are not a single material. It's a complex material system. There is a substrate material, there is an oxidation-resistant coating. Over the oxidation-resistant coating is a thermal barrier coating. And we have to understand the micromechanical behavior of this material in relation to the loading of this complex material system with very heterogeneous set of properties. So we have to understand the behavior of these individual materials in the system. And to understand that behavior, we have developed special techniques to evaluate materials at the small volumes that constitute coatings, system, and so on. And we have applied that knowledge into understanding the overall behavior of the system. Okay. Let me move on to titanium used in the front part of the engines. And I want to remind you that we have some of the largest resources of titanium in the world. And this is found as black sand, which is found on the beach sands of Kerala. It's ilmenite ore, which is a iron titanium oxide ore. And we have developed the technology at DMRL, transferred the production technology to KMML with ISRO support to create this facility for producing titanium metal from its ore, which can now be used by Mithani and other organizations in this country, both private and public, to produce the kinds of shapes and sizes and forms that are used in aero engines. So we are fairly mature in this titanium technology, starting from ore to final product. Okay, and we understand the relationship between composition, processing, and properties quite well in this material. At the end of the engine, we are looking at these silicon carbide-based composites. And somewhere in the early 2000s, while I was still the director of DMRL, we supported a national program to develop these silicon carbide composites. So this involved making fibers, this involved weaving of fibers, this involved infiltration of fibers, and certainly in the National Aeronautical Laboratory, set up these facilities and capability for infiltration, which NAL has developed quite extensively. And so through the support of subsequent programs, NAL has been able to develop these shapes, which represent the convergent divergent flaps in an aero engine. It has been able to understand the structure of the material and the coatings on the fibers as it relates to properties, and these are fatigue properties actually measured by Kalyan Sundaram at NAL. And these are collaborative programs between IIT Kharagpur, NAL, supported by gas turbine materials programs of the Aeronautical Research and Development Board. Where do we go from here in these composites? If you want to migrate these composites into the turbine section, and there are very good reasons for doing so. You want to migrate these composites into turbine sections because these materials have a higher temperature capability than nickel-based superalloys, and they're lighter than nickel-based superalloys. And because they have a higher temperature capability, they need not be cooled. And if they do not require cooling, then you don't have to extract work out of the compressor to drive cooling air, and therefore you improve engine efficiencies. These materials must also have coatings to withstand oxidation resistance. But very importantly, you can't use carbon fibers. You have to use silicon carbide fibers in these silicon carbide composites if you have to migrate these composites into the turbine section, because carbon fibers do not have the oxidation resistance that are required for long-term applications in aero engines. Okay, so I don't know what's going on here, but anyway, one of the disappointments I think I've faced over my career, that in spite of sustained effort and funding, both to NAL and DRDO labs, DMSRD in particular, we have not been able to develop the technology of making these silicon carbide composites. And this is unfortunate, but I hope over the next decade or so, this technology will emerge as well. Okay, I have a problem. I think I'm not able to change. Okay, good. Finally, and I want to conclude with a slide of 2 or 3 slides to remind you that structures and materials fail in application. And this, of course, NAL knows extremely well. One of NAL's significant capabilities is the understanding of failure analysis of materials and the origin of failures. But what we do in this regard, and this is being done at DMRL, at GTRE, and so on, is to understand the effect of service, and NAL, is to understand the effect of service spectrum component loading and materials properties on failure probability assessment. And this is an extremely important part of material science and engineering, combined with the in-situ health monitoring, which Ramesh is going to talk about. And remember that the majority of critical materials actually fail by fatigue, by and large, okay? You then have to develop, in combination with all this, and a good life extension philosophy, both for new materials, both for legacy materials, and indeed a lifing philosophy for new materials. So all of this is quite a distinct material science and technology and structural mechanics and health monitoring endeavor that must be pursued over the coming decade or so. Where are we going finally as materials engineers? I've tried to bring together the elements that we as materials engineers are now trying to combine in processes that will allow early materials insertion into practice. So we look at gradient structures for optimized properties. We look at topology optimization for functionality. We combine these with the advanced manufacturing techniques. And supporting all of this is the integrated computational material science and engineering effort, which includes creation of materials processing performance databases at scales that are relevant to the application of these materials. And this combined platform, rather than looking at each of these as individual elements, which we've tended to do in the past, we hope will accelerate materials insertion into service. We have tried to support the materials ecosystem in aeronautical engineering through the Aeronautical Research and Development Board. And I want to particularly refer you to the gas turbine materials and process program, which we initiated about 5 years back. So the idea was that there is this interaction between the operational environment at one extreme, the systems environment somewhere in the middle, and laboratory research and proof of concept work and the other. And the idea was in this program to look at these areas in this intersection between the systems environment and the proof of concept work that can go on in universities and our R&D laboratories, NAL included. And we've done a fair bit in this area. And I'm sure many of you at NAL know this program quite well. So with that, I want to thank you again for giving me the opportunity to talk a little bit about materials in general and the way we as material science and engineers do our work, the way we integrate with the structural mechanics people who actually design structures, and the way we combine this interaction in what we have done with aeronautical materials in this country. So thank you very much for your attention.
Thank you, sir, for a very interesting and informative lecture on materials for flight. I now request Dr. Sridevi Chade, Head CSIR 4PI, to introduce our ACSIR speaker, Dr. Ramesh Dharam, please.
I will take, and you have to excuse me for Ramesh's talk, and I'm sorry, Ramesh, that I cannot be there because I have to go to another meeting, but thank you.
Thank you, sir. Thank you for joining us today.
Good afternoon. Chief guest is logged off, so good afternoon to Director NAL, my colleagues from CSIR-NAL and CSIR-45. So today is the Science Day, which we are celebrating along with CSIR-NAL. Actually, there are two programs in it. One is the Science Day celebration, which just, am I audible? Science Day celebration, which just now we heard a lecture from the chief guest. And the other one is the ACSIR celebration. ACSIR, for the first time, they're doing the Science Day. Both the ACSI Academy of Council of Scientific and Industrial Research of both CSIR NAL, both the coordinators, and CSIR 4PI are doing this thing. They actually came to me, I think 15-20 days back about this program, and they conducted few competitions for which I think they're going to announce the prize after the lecture. And it is 10 years since 10th anniversary of ACSIR. So they are starting a lecture series for ACSIR. So today is the beginning of the lecture series, and they have chosen Dr. Ramesh Dharam from NAL to begin this lecture series. After his lecture, I think they're going to have the prize announcement of all the competitions done for both NAL and Fourth Paradigm Institute. So I have a very long introduction of Ramesh Dharam, but since all of you know he's from NAL, he's not an outsider. I think I will make it short. If I miss something, I think it's okay. So he has done his PhD from in polymer science from University of Akron, Ohio, USA, and he's been in NAL since 1992 till date. And he's in the Advanced Composite Division, ACD. And he was former president of Indian Society for Advancement and Process Engineers. And he has got several awards to his credit. And he was also elected as a fellow of INAI in November 2021. And its areas of interest are health monitoring of composite structures, processing of composite structures, 3D composites, and thermocomposites. And during his tenure in ACD, it has been recognized as a center of excellence for composites. And he was the coordinators for 2 consecutive years. That's what I got from the biodata. And there are several awards, maybe 1 or 2 I can say. The division during his tenure, the division won the 7th National Award for Technology Innovation. And he has 2 patents with co-authors. The patents, one patent is on process for manufacturing co-cured composite structures and products manufactured thereof. And the other patent is a system and method for visualizing real-time resin flow front in resin infusion technology for manufacturing composites. Yeah, with these words, I welcome Ramesh Dharam to give you the first lecture series of ASMS.
To all of you. It's indeed a privilege to be here. Thank you to Dr. Banerjee and Director for inviting me. Also, it's really nice, after nearly 2 years, we're actually coming on stage and are able to talk. We've been just looking at the screen for a long time, and it's definitely a different feel to come on and think. So what I talk about is we have, over the last 2 decades, our team has done a lot of work on health monitoring of structures, especially composite structures. And this is the team. It's headed by Mr. Nitesh Gupta, and a lot of other scientists, colleagues over the decades have worked. We have done some interesting work, and I thought I would take this opportunity to share it with all of you today. So, what we are really aiming at is, can we build and intelligence at least somewhere 10% or 20% as close to our human system. They want sensors, response, to be able to diagnose, to be able to prognose, and what are all the different kinds of things that are going on in our system? Can we put those into our structures that we are flying today? These are, I think we are still far away from this right now. And if you look at the health monitoring universally, there's a huge requirement. You look at the wind industry, the train, shipbuilding, everywhere. The health monitoring is progressing rapidly, and you can see the kind of estimates getting $3 billion US over 30. Every year there's a 30% growth from 2016 to 2023. And our focus is primarily on the aircraft, and within the aircraft, we know that structures are probably at a lower level of requirement of health monitoring. Engines, avionics, and several other complex systems have very challenging requirements. And within the structures, we are looking at some of the composite structures and what is special about these composite structures. Why do we need health monitoring? What benefit will this health monitoring give? And if you look at the structures that have been made, I'm very happy to say that for both in that combat aircraft and Saras aircraft, NAL and in particularly ACT have made a lot of contributions for these programs. And what we have developed are highly procured structures with a lot of integral construction. So what do I mean by that? You can see a large number of structures have been developed, and we're also happy to say a lot of this has become production technology today. We have tied up with Tata Aerospace Systems Limited, and nearly 40 sets, 35 sets of parts have been supplied by them for the program. And we've developed a large number of parts for the Saras aircraft, and now we are increasing. Some of the fuselage also will become part of the next generation Saras. So when we look at these composite structures, what do we mean by integral construction? You can see the fingers, the skin, or the ribs, they're all made in one single shot. So where is the weak point in this? This is the interface between these two. If there is a D bond in these, primarily we would like to know ahead of time. And also what happens in such large structures, if you look mainly, especially if you look at a wing or some of these structures, what are the principal kinds of damages that we are faced with? It is mainly kind of an impact damage that the composites are really bothered with. How does this happen? You can have a tool drop by people working on the aircraft. It can be aircraft debris. It can be hail. It can be lightning. Varieties of different kinds of damages can take place. And one of the interesting things about composites is it looks very nice from the outside. But whereas you could have a lot more damage within the structure. And that's why these are called BVIDs, barely visible impact damage. So when you look at it from the outside, you hardly even know that there is a damage inside. So it is all the more important to be able to find out what is this damage in the structure. So these are some more composite structures. This is developed by the infusion technology, and you can see nearly 334 individual parts have been made as one single part. So when we look at an aircraft health monitoring or inspection that is being done today, several. You have daily inspection, fit checks, B checks, C checks. So there is a lot of money involved in inspecting these structures. So this is called a periodic maintenance. So the paradigm shift that the world is looking at is, can we move from this maintenance to a maintenance on demand? Can I have sensors, can I have systems that will actually tell you the state of the structure, the health of the structure, so that I can go and inspect it when I need to inspect it and get away from this periodic maintenance, the overall goal. And so if you look at the present aircraft, you can see practically there is really no health monitoring in place. And so you have everything takes place. You after the aircraft lands, you find out what has happened to it, what is the damage, and then you try to fix it. What is in the next generation is, as it is flying, can I get the information on ground? So before the aircraft has landed, we know that this is the kind of damage, this is the kind of problem, and this is not only applicable to structures, it's applicable to all kinds of problems on the aircraft. So as soon as the aircraft lands, I can fix it, and you can see that you save the time. What is the future generation is, I have all the prognostics built in. I continuously have all the information. I know when I have to really inspect it. I don't really have to inspect it at all here. I know what the life of the structure is. I can go and fix it later. And so you have a huge time window that you can save if you can have a complete health management system in place. And so one is a reactive approach where you just get information and then you move to a proactive approach. So when we want to do this, it is quite a complex system because you have a number of challenges that have to be addressed. First of all, what are the sensors? You have so many different sensors that you can choose from. Which sensor should you choose? How do you integrate these sensors into a structure? How do you collect the data without loss, without any false negatives, without any false alarms that you're going to give to anybody? How do you build a robust system? These are all the challenges that one has. And so when we look at the various kind of sensors, what I'm going to be focusing on today is, we have done a lot of work with fiber optics. And this is just, for all of us, it is just the normal optical fiber that you see, which we are using for the communication purposes. It is something very, very similar to that we want to use. So what is the advantage? It has lightweight, small in size, very easy to integrate into a structure. So this is where we are talking, the composites become amenable so that we can embed these if you want. You can do surface bonding if you want. And all these, since they operate in the optic domain, they don't have any EMI interference, electrical interference, the power consumption is very low. But with all this, the real thing that we are battling today is, does it make a business case with the way we are designing structures today? So there are several technologies over the last 2 decades worldwide. Within India, we have had several programs that are going on. And you can see the oldest is the resistive strain gauge. We have piezo-based sensors. I'm going to talk about the DFOS. There's a technique called the CVT, the fiber flag rating, and so several such technologies. So one is, we can have a point sensor or a distributed sensor. A point sensor is, I can have certain sensors where maybe in a large wing I have 10 or 15 or 20 different points I can get information. So how do we, what is the sensor readout, the installation, how much coverage am I getting using this? Then we have distributed sensing, where I'm going to tell you the entire optic fiber will become a sensor. I can get the strain from every 5 millimeter within the fiber of the sensor. That becomes distributed sensing. Electrical versus optical sensing. Active versus passive. So this is also, if you want to do online health monitoring, can I get information as it's flying? On the loads, on the damage. Passive is, after it lands, based on I send a signal, I interrogate the structure, then I get information, and that I can find out the state of health of the structure. So very basic, a fiber is, it has a core and a clad, and then based on the differential refractive index, the light just gets reflected and goes through from one end to the other end. That's the bare optical fiber. And so what we have, you can have different kinds of sensors. I will not get into those details. You can have a sensing element at one end, or you can have a sensor at a predefined location on the fiber, or like I said, it is sensor, when most of the fiber itself becomes a sensor. So we have been working with what is called as a fiber Bragg grating, and essentially you take an optical fiber and you can use a UV laser and you can write gratings within the fiber. This is probably about 10 mm in length. And so there is a periodic variation in the refractive index. And so when you launch a certain wavelength of light, at this point, most of the light will get reflected back. So this is the reflected spectrum. And you get a shift in the wavelength. And this shift is a function of both the strain and the temperature. So this is the basic equation. When you do either tension or compression, this wavelength will shift here, and it also shifts due to temperature. So this is one of the problems that we have with the fiber optic sensors, that they are sensitive to strain and temperature. So when you have to do these, you have to develop different algorithms to also compensate for the temperature shift. And I will not get into how the FPGs are fabricated today. The other important thing is, how do you package this? You have to see that when I'm measuring both strain and temperature, like I said, how do I compensate for the temperature? Because most of the times we are interested only in the strain. You can have acceleration, you can measure pressure. And so how do we pack all these things into our system? The other aspect of this project, we did a number of projects with DISMAS from ADA, and then we did the programs under AR&DB. So we had certifying agencies also involved, and they wanted to know what is the effect of all these fibers, though they are in small quantity, if you incorporate them into the composites, is there any problem? So we had to do a lot of property testing at both room temperature, high temperature, static testing, fatigue testing, and we showed that there is no problem. And more or less from the certification agency, we got the approval. And these are all the host of specifications that one has to choose when you want to choose your fiber Bragg grating system. These are called the interrogating systems. Primarily, we have also had programs within India where IAC, CSIR-NAL have also tried to develop these systems. So this is from a company called Smart Fiber, and you can see these are very, very light. This whole thing may be about a kg and a half, and you can have 4 or 2 or 8 channels. Within each channel, I can connect a fiber with as much as 16 sensors, but that will depend on the level of strain that you want to measure. So typically we go for 4 channel systems, and in each you can connect a fiber where you can measure about 6 to 8 sensors. Then we have, we somewhere in 2009, we also came across this technology, which has its own advantages. The entire fiber is a sensor. What we are really looking at here is a Rayleigh-based backscattering. So actually, when the light is launched, there is every point of the fiber predetermined, you get a backscattering back into the interrogator. And so you can actually find the strain. If I have a 10-meter fiber, every 5 millimeters, I can find the strain at that point. So this is a phenomenal application. If you have a simple cantilever beam, you can see if I put a fiber, I can get the entire strain profile from one end to the other end. So I'm doing a static test. You can all see we're doing a lot of static testing. This is the kind of wires that you need. You can dispense, even for our testing purposes, use this kind of technology, and you'll be able to save a lot of cost in both the paraphernalia and the number of strain gauges. So I have a simple panel here, a stringer panel. This is a skin stringer panel. And we have put the distributed fiber. I think at least the people here can see it. There is a fiber going like this, on the front side of the panel, and again on the back side. So with this one fiber, we started compressing this panel, and as it compresses, so you can see as the panel is getting compressed, you can see this is where the loose fiber is, and so you will see no strain, and this is the strain in each fiber from this end to this end, and again from this end to this end. You see the strains, and all these are bubbles where the buckling occurs, and you can beautifully see how with the single fiber, the entire panel, you can capture the buckling of a panel. So it's a phenomenal tool that you can use for testing and easily tell you what is happening when either in flight or when ground or in testing. This is a huge technology that can be used. And already there are applications. NASA is using this. Most of the UAVs are already using this technology in Israel, where they put the entire fiber on the wing and you can actually monitor the strains. And you can also monitor the change in shape. And one of the problems with the optic fiber is it's very brittle. If you turn it around the radius, it can break easily. So how do you package these? How do you integrate these into the structure? So you have to find soft ingress egress points. And so all this we have done over many programs, and now we have got very good packaging systems available for putting these onto the aircraft. Now when you broadly see health monitoring, you can have two broad classifications. Either I want to do it in flight or I can do it on ground. And when I say in flight, I want to acquire all the data in flight. The instrument is inside the aircraft, I record it over there, and I can choose either to do the analysis there or after it lands or remotely transmit via telemetry if it's a UAV. These are the choices. The other choice is I put only the sensor on the aircraft. And when the aircraft lands, I take a measurement. And this, based on these data, I give a decision on whether there is a damage or not. This is today probably a much easier thing to implement because I don't have to put many systems on the aircraft. Certification, so many problems can be avoided, and I can have just a system on ground, instrument the aircraft, and this is what we are doing we have a program with ADE for the Swift UAV. We have done this. We are awaiting flight trials. So this slide just shows you that the most important damage that we are looking for is the impact damage. So suppose I have a 30 or 35 meter wing and somebody just comes and drops something on the wing. Can I tell that I had a drop? So there are different levels. Can I tell something is wrong? Can I tell where is the location? Next, can I tell what is the damage size? Then can I also say something will go wrong soon? So these are all up to level 4 is what we are hoping we can do, or we have done quite a lot of it. Level 5 moves to self-diagnosis. Level 6 is self-healing, where they actually put fibers and they put the resonant hardener within it. It senses that there is a crack and it ruptures and it heals. So these are probably a lot of research is done in these level 5 and level 6, still not there at the aircraft level. So once we do all these, collection of data is one thing. There's a lot of signal processing we have to do, a lot of algorithm development using ASS, ANN networks, SVM. We have a fantastic group and a large number of students who are actively working on this. Very briefly, let me take next 5-10 minutes on what we have done at NAL. Like I said, we have done a lot of studies. I mean, what I'm showing you is that just snapshots of slides which I've actually taken quite a long time to do. A lot of sensor characterization. Then we have done how to install these sensors. What is the kind of instrumentation needed for both flight and for offline? How do I route these fibers within an airplane? How do I have connectors to connect it to patch cords? So these are all the, this is a system that we have actually done on the Nishant UAV. And we have done a lot of ground tests as well as flight tests. So let's take a simple case of a test box. This is a top skin which is having three, you can see there are three spars running, and only in the middle spar we have created a debond. And we have not told the person that there is a debond. And we have put these sensors onto that. And as we load this, you can see there are three spars here. This is I spar, C spar, and then we load it, and we've got these sensors in there, and then we capture the data, and the straight line is the healthy line. And so you can see as we get closer to damage, the strain is a function of the change in stiffness, and you can see the change, and very easily we can capture that there is a damage. But one of the problems is the change in strain is very local. So this is one of the challenges. The sensors have to be close to the damage. So how do I make a network of sensors that are close enough to capture this? So you can see this is the 150 mm debond, and you can see the healthy to the unhealthy, you can easily capture. And we do this using FEM, where we create the healthy networks, we do unhealthy networks with FEM, do all the training, then build all these algorithms. And the results here, we look at, first of all, location. It is very important to first get the location right. And we have done a number of algorithms, triangulation, scan-based, to get the location. You can see the debond is located at 380 mm. And also, this is a function of loading. When the aircraft is flying, it is loaded at different times, at different levels. Can I find it out at all the different loadings? So you can see here, I've loaded only 500 kgs, and here it's 3000 kgs. And you can see very close correlation to the location. Similarly, the damage size is 200 mm, and you're pretty accurately being able to predict what is the damage size. This is again for another case where the debond location is at 355, and the damage size, this bond size was 150. When we were part of the Center of Excellence under there was a program called ACE-COST, ARNDB Center of Excellence for Composites. So we had a program with this. Can we immediately, when the impact takes place, as soon as the impact is taken place, can you find out the location and damage in a structure? So we did a lot of studies, starting from flat laminates to stringer panels, and I think they have not put the box levels, and for all we can see the probability of detection at nearly 90%. Within 50-60 mm, you can find out the location. So imagine I have a 10 meter or 20 meter wing, and if I can tell you the location of a damage within 50 mm, I think it's a marvelous technology which we have. The key challenge is still how closely we can find the damage sites. And this is using the distributed fiber. When you actually look at the signal, you can see there is not much difference. So there's a lot of intelligence the team has put in to develop the algorithms to how to do this, called successive differentiation, to find out all these damage sizes. And I have one more video here. So you can see here, we have this side we have a drop. The weight is getting dropped, and instantaneously it tells you here the location. So the weight drops, and immediately you know where it is located. And all this was demonstrated and this technology, as part of ACE-COST, we successfully developed and showed it to them. We've also done flight trials where we mounted the sensors on the bottom spar cap, and Nitesh here actually flew with the pilot, and this is where the sensors are put. A number of flight trials were done. We got good correlation between the strains measured and through the FEM. Another interesting project we had was along with ADE and Israel Aircraft Industries and Tel Aviv University. The thing was the boom of the Nishan. Can we instrument it? Can we put this sensors and the acquisition system and actually get the data? The Nishant is a very interesting animal, and okay, you can see it is a catapult launched. Okay, it launches in a catapult, then after flying for some time, and you can see all the strains are getting recorded. And of course, this is the camera that we have nothing to do with that. I mean, that's the Nishant is taking the photographs. Then it is open to the parachute and it lands. So interestingly, when we did this around 10 o'clock in the night, it actually crashed into a field. So we all went at around 9:30, 10, very worried whether we actually captured the data. But the entire system, we had made such a rugged way of putting the system in place. With all that, the entire data was captured, and we got the flight data, the catapult launch, the parachute recovery. In fact, we also showed a buckling of one of the booms taking place. So quite a lot of work has been done in flight also. A number of tools of quick view, impact view. Nitesh loves all these, fancy names. Diagnose view. A lot of this has also been copyrighted for the software. We are moving into another technology called visual inspection. Can I just have quadcopters go over the aircraft, take pictures, and tell you the health of the structure? So our team has done some work, and a lot of this is going on in Airbus and all the different manufacturing companies, because this probably will become the best business case. Because I don't have to put any sensors on the aircraft, I don't have to fly any instrument on the aircraft. When the aircraft lands, I just have something flying over it, collecting images and telling you the health of the structure. So we have done work on this, where actually you take a projector and project a pattern, and then you study the fringes. You can actually capture the dent depths very well. In composites, once you know the dent depth, then you can correlate with, for that thickness, you can actually correlate what is the damage within the structure. So this is an interesting area we are pursuing, and of course we have not progressed too much, but we have done initial studies which are very promising. Several issues and challenges are there. You have to look at what kind of damage, how to put these sensors close enough, reliability, you don't want any false alarms, field trials, certification, and the business case has to be done. Quickly, I'll take 2 minutes as a byproduct of what we have done. We got a very interesting offer from a company. Railways is looking at a huge challenge of using sensors. So they want to do cyber signaling, trigger sensoring for a thing. Essentially, when the train passes today, somebody is actually seeing and saying the train has passed. Can this automatically say the train has passed and I can signal? Can I tell the wheels, as the wheels go, many times they have defects. Can we monitor and tell there is a defect in the wheel? So we have done in the last 6 months, very short time, our team has put these sensors on the track. There's a company called L2M, that's lab to business, lab to marketing, L2M lab to marketing. And you can see these are the sensors we have actually put on the wheels. And you can see we have put sensors like this, and that is just the packaging done here. And we have collected the data. Number of, because every day so many trains go, we've got very repeatable data. And they are also very excited because they've worked with a lot of imported sensors from China and nothing is repeating. And none of these technologies are available from abroad. So what is the requirement? They have something like 8 lakh sensors needed, the rolling stock, number of structures, something like a $1.6 billion business. And railways is now looking and to see how to encash this. And so we also are looking at a collaboration where we can use our FPG technology, which we used for aircraft, and put it to the railways, and where we can make a substantial difference to the health monitoring of railways in the future. I think with that I'll end. Thank you all. This is by our large team. Though we say health monitoring is a small team, we have people who do the ND, the coupon level testing, structural testing. A large number of people in the division are involved in these projects. And that's why I think it makes it a very good composite. Thank you very much. Any questions? Any students have any questions? This is what they have studied. No. This is what the company has made a market survey. This is the kind of investment if they put, and the person is on the railway board and they're interacting. If they do this, this is the kind of business they can get. It's a projection by a company. Lab to marketing. Yes. Actually, we have seen, because when this huge weight goes of all these wagons, that's when you get those strains. And if there is, the whole axle is getting monitored. And if you have that defect, later we can process and we can see some changes. We have seen some studies, we have not got data. There could be a small break in the wheel, may not be a crack. Sometimes they have those chips which they don't check. So there is, the end of the thing could have been broken off. So different kinds of problems, which literature is saying there is potential. But we have not yet measured that data. But who will go and check? No, who's going to go and check those wheels? Imagine so many trains, so many wagons. Who's going to go and inspect all the time? Yes, but when it is passing, every time it passes, you'll be able to see, hopefully. We have not done this yet. We are hoping that's the study we have to do. Generally, larger defects. Yes, abnormality in the wheel. See, what we know in the composites is, first of all, very small defects, nothing will happen. So when you have typically a dent depth of, let's say, 1.5 mm for say some function of thickness, so those kind of dents cause larger damages inside. So we want to only capture something like 1 mm, 1.5 mm, 2 mm, which you generally may not you may miss, or an inspector has to go carefully and see and inspect. Surface. No. On the surface. So on the surface, you will see a dent. If we take our laminates, we get a small dent. But inside, you'll find something like 1,000 millimeter square damage. So dent depth is a very good way of finding damage within our structures.
I have one question. This is it real time? The data is real time.
Which data?
It is not just it happens that time, and it is forwarded after that. That is
No, which one are you talking about?
the structure. So that
Okay. See, now there are two ways. One is if I have my fiber Bragg rating sensors and they're always measuring, then when some event takes place, it can capture immediately. Whereas sometimes there's already a damage that has taken place. You bring the structure and then you load it. Then I can measure the data and I can tell you the what has happened to the structure. So one is active, one is passive. Does that answer your question or no?
yeah. So like in aircraft structure, for example, we put it, and then because the load some
It's online. It will be continuously measuring.
continuous.
Yes, yes.
But then one aircraft comes in the normal land type. Then it will go away.
Yes.
Then after aircraft lands it, then you will be analyzing what incident will happen. Then
Yes, actually, we don't want to, I mean, the ultimate goal, like I said, level 6 is where it can automatically do everything. But our present goal is when you land, you measure it, and over a, you can keep checking. Every thousands of flights, 2,000 flights, you can build software to check the data and tell if there is an anomaly. And then only tell the maintenance department to look at it. So you don't have to they need not worry. It's like saying once I detect an anomaly, then I can go for an inspection. Until then, actually most of the times you're not finding anomalies. Simply we're going inspecting and seeing, yeah, nothing is there, and the entire time is wasted. See, the types of defects in composites are different. The types of defects in metal are different. Okay, so in an engine, what kind of defects come, how fast it will grow is a totally different picture. You have to go to the metal specialist to find out when all this happens. In the composites also, when you have an impact, it has delaminations, it will have disc bonds, and we have designed for what is called as a damage tolerance approach. So up to a certain time, it will not grow. So it's very difficult to say. You can't just say this will grow first or this will grow fast. There are totally uh, two different things we're talking about. Anything else? Anybody? Okay. Thank you very much.
Thank you, sir, for an insight for structural health monitoring. I now request Director NAL, Head 4PI, and Head KTMB to occupy the seats on the dais, please. I request Dr. Vanaja, ACSIR Coordinator, CSIR-NAL, and Dr. KC Gowda, ACSIR Coordinator, CSIR 4PI, to conduct the prize distribution program. Respected dignitaries on the dais, ACSR faculty assembled here, ACSR students, and my dear colleagues. Greetings to all on National Science Day celebration today. ACSR is celebrating its 10th anniversary also. And as a part of Azadi Ka Amrita Mahotsav, we have conducted certain programs to inspire the students. The category of competitions: essay writing, poster presentation, and then a cartoon, theme-based cartoon, and CSR 800 project, which is the curriculum included very recently. To inspire the students, we are instituting the best societal project also. These are the categories of programs that we have organized. And I request Director NAL to hand over the mementos to the prize winners. Students are requested to come and collect the award. Essay writing competition. The first prize goes to Irana from 4PI. The second prize goes to Miss Amrita. Miss Amrita from NAL. The third prize goes to Rani Devi of 4PI. The third prize is shared by Mr. Viresh Gowda, NAL. Mr. Abhinav Kumar from NAL, Consolation Prize.
favoring the camera.
Mr. Chandru Krishna from NAL, Consolation Prize. I request Dr. Sridevi Madam to distribute prizes to theme-based cartoon drawing winners. Anina Anju from NAL first prize. The theme for cartoon is impact of COVID on lifestyle. Certain cartoons are placed outside this auditorium. We can go through. Amrita V, second prize from NAL. Irana from 4PI, third prize. Ajay Bankar, consolation prize from 4PI. Raghavendra Prasad Babu from 4PI, consolation prize. There was a poster presentation with the theme Science Behind My Research. I request Dr. Ramesh Dharam to hand over the mementos to the poster presenters. Rani Devi from CSR 4PI, first prize. Chandu Krishna from CSIR-NAL, second prize. The second prize is shared by Ms. Tejashwini Chandrakant Gowde from CSIR-NAL. Smriti Parwar, third prize. Nikhil Kumar C from NAL, consolation prize. Thank you, sir. I request Dr. Manju Prasad sir to distribute the certificates and mementos to the people who have presented CSR 800 projects successfully. Ms. Rani Devi. Chandu Krishna. Sharon Gowda. Mr. Veeresh Gowda. Ms. Adila. Ms. Niranjan. Umesh. Ms. Bhavya. Ms. Amrita. Ms. Anina Anju. Ms. Tejashwini. And Smriti Purva. Thank you, sir. To organize these competitions, we had a 8-member jury who has given their valuable time, and they have judged all these competitions. Now I request Director NAL to present some small mementos to all the jury members. Dr. Gopalakrishna Patra from CSIR 4PI. Dr. Imtiaz from 4PL. Dr. Venkateshwarlu from NAL. Dr. Kota Salman Raju from NAL. Dr. S.T. Aruna. Dr. Sandhya Rao. Dr. Latashri. Dr. Jane Balaraj. Thanks. ACSR is felicitating both the speakers of today's lectures. I request Director to present a memento to ACSR lecture speaker today, Dr. Ramesh Dharam. I request Dr. Panda sir to collect the memento on behalf of our Science Day lecture, Dr. Dipankar. To conduct all these programs, we were constantly encouraged by our ACSR Senate member, Dr. Sridevi Jade. I requested Director NA to present a memento to Dr. Sridevi Madam on behalf of ACSR. As an expression of gratitude for organizing all these programs, I request ACSR Senate member Dr. Sridevi to present a memento to our directors, Jitendra sir from ACSR. And there was a constant encouragement, consistent support from ACSR functions. I request our Senate member, Dr. Sridevi, to present a memento to Dr. Manju Prasad. And for the constant support and encouragement to organize science functions and science-related activities in NAL, I request Dr. Sridevi to present a memento to Dr. Panda, Chairman of Academic Cell. Thank you, madam.
So I've been given a small job. Basically, we have got so many mementos from everyone. So the people who actually organized this from beginning, planned, organized as part of Azadi Ka Amrit Mahotsav, the two coordinators of ACSR coordinators of CSIR and NAL. I request Director NAL coordinator Dr. Vanja. Okay. It was a nice thing to do it for the first time, and from my organization, Dr. K.C. Gowda, ACSI coordinator. He's serving the second term. Lot of work.
Thank you, madam. Thank you, Dr. Vanaja, for conducting the prize distribution program. I now request Dr. M. Manju Prasad, NKVMD, to propose the vote of thanks.
First of all, I would like to wish you all a very happy National Science Day. It's a very happy and occasion for all the scientific community of the country. And as you know, CSIR has been celebrating this for years, and it's a wonderful opportunity for us on this occasion to listen to very special lectures and very special people, probably whom we will not hear otherwise. And in that context, today we had the opportunity to listen to Professor Dipankar Banerjee, who readily accepted our invitation to give the National Science Day function, Science Day lecture. He is the former director, DMRL, and presently he is a professor at the Department of Materials Engineering, IIC. On behalf of the director, NAL, and on behalf of all of us, I would like to thank the professor for sparing his valuable time and giving us a wonderful lecture on material science. He took us almost from the primitive development of material science to the latest developments, including the issues involved, challenges involved, the processes required, and so on. So thank you, sir. So I'm so happy this time our National Science Day celebration has become special because of the involvement of ACSIR and the students of ACSIR. Especially I would like to congratulate all the faculty, all the coordinators, the faculty and the students of ACSIR for actively becoming part of this National Science Day celebrations, because I think the real science starts. The real science starts with the work of the students. That is where the real seed starts germinating, and the plant starts growing. And I'm so happy that this has become part of the ACSR activity. The ACSR activity and ACSR has become part of our National Science Day celebration. And this celebration has been earmarked with a special lecture, a special ACSIR Science Day lecture by Dr. Ramesh Dharam, our head Advanced Composite Division and the cluster chairman Structural Technologies. He gave us a wonderful lecture on the structural health monitoring and how the health monitoring concepts and techniques are being used for composite structures. Thank you very much, sir, for spending your time and addressing us. I am sure his lecture will be a sort of an inspiration for many of the student community and many of the young scientists who would like to specialize in that field. I would like to thank our director, Jitendra Jadhav ji, and also Madam Sridevi Jade for having supported actively supported for celebrating this function, because without their active support, this function cannot become successful. Thank you, sir. Thank you, madam. I would like to thank Dr. Vanaja as ACSR coordinator and Dr. K.C. Gowda, ACSR coordinator from 4PI, for taking all the initiatives and leads for organizing the competitions and making ACSR a part of this celebrations. I would like to thank my own KTMB team members for taking all the pain and efforts to ensure that the function goes smoothly and everything is in order. Thank you all. I would like to also thank the ASISD team members who ensured that the audio visuals are all maintained in a perfect way and everything went on very well. Thank you all. Also, I would like to thank our director's office, our HLS, and our service divisions involving the EBU, electrical, and all other divisions who have actively contributed for the successful conduct of this program. Also, I would like to thank all the invitees, both offline and online, who have attended this function and made it a grand success. Thank you all. And I think there is an announcement. We have to conclude this program with the national anthem.